This is the next video in the series about acid and base strength. We have talked about strong acids and bases, weak acids and bases, and conjugate acid-base pairs, and which one of the two is going to be the strongest in a particular case. And so now we're going to use the information that we know to solve for the pH or the K value for a particular equation using an ice table. We have really beat ice tables over the head in the equilibrium chapter, but there's a couple of new features involved in interpreting the question and about incorporating the pH and the pOH into your table. So examples will follow here. And we're going to start with this example because I wanted to do that one first. Okay, so this example says we have 0.950 molarity solution of ammonia with a pH of 11.62, and we need to find the Kb. So a lot of information here, molarity, pH, and we want the Kb. And so first of all, when we make our ice table, which we are going to do here, we need to know if NH3 is an acid or a base. And maybe you remember because we talked about it in the last video, or maybe you don't because maybe this is some random compound that you've never heard of. And at some point, these compounds that we use in acids and bases will start to sound familiar, but until they do, you need to have another way to predict what it's going to do. So the pH here can indicate to you what this is. So the pH is 11.62, and that is greater than a pH of 7. And if you remember, that means it's going to be a basic solution. And if NH3 is the only thing in the solution, then NH3 is going to be a base. And it isn't on our super short list of strong bases, so it's going to be a weak base. So if it's a weak base, when we set up our ice table, we're going to use the base ionization reaction as our equation at the top. We got to know that one by heart, or we've got to do it for NH3. So let's be specific this time so you can see what that looks like. So ammonia plus liquid water sometimes goes to ammonium and hydroxide. All right, let's plug in information that we know. So we're told the initial ammonia solution is 0.950 molarity. And we also have this pH. And pH isn't a concentration, so it doesn't go in this table, but we know that pH is related to H3O plus concentration. And we see that we have OH minus concentration in the table. And if you remember that cool box that we made up a couple of slides ago, we can use that to convert. See if I can find my box. Here we go. So we have the pH, and we want to get the OH minus concentration to put in our table. So I think that we should go in this direction. We'll find H3O plus, and then we'll find OH minus. And again, it doesn't matter which way you go around the box, as long as you get the right answer. So we're going to turn pH into H3O plus concentration first. So our pH was 11.62, 11.612. That equals the negative log of H3O plus. And remember, when we undo a log, we're going to do the base, which is 10, to the exponent, which is negative 11.612, because we moved the negative to the other side first. Math happens here. And we should get 2.443 times 10 to the negative 12th molarity. Super small number. So the pH always represents equilibrium. So that means that this is going to be the H3O plus concentration at equilibrium. And what we really want is OH minus, so we can put this in our table. So we remember the second step from the box is the hydronium concentration times the hydroxide concentration is equal to 10 to the negative 14th. And plug that guy in right there. Math happens here. We should get 4.093 times 10 to the negative third molar. Oh, an awful lot of work, and we haven't even finished the table. Okay. So this value for hydroxide is going to be the equilibrium concentration, because pH is always about equilibrium. So this is going to go in the bottom row of our ice table under hydroxide. So 4.093 times 10 to the negative third. It's kind of a long number, so you want to leave plenty of room in your table to write this a bunch of times. Okay, and now that we have a number in the initial row and in the equilibrium row, we should be able to solve for everything else. So let's see. We know the initial concentration for ammonia. We don't need water. We know we're initially going to have 0 of ammonium and approximately 0 of hydroxide. Then we are going to shift. We're going to shift towards the right side. So we're going to subtract on the reactants. We're going to add on the products. And the amount that we're going to add is this number, right? Because this would be plus X and minus X. We'll write it really lightly here. If we did 0 plus something to equal this number is equal to something. This number is equal to X. So it's going to be plus 4.093 10 to the negative third. And also over here, because they have the same stoichiometric number, and also over here with a minus sign. Okay, and then we add down. So you may need your calculator for this one. 0.95 minus 4.093 10 to the negative third should be 0.946. And this one's easy. You're just adding 0. Okay, that was an awful lot of work. But we got what we wanted. We filled in the E column with numbers, and now we have enough information to solve for K. So our KB is products, ammonium times hydroxide, divided by reactants, ammonia, so it's going to be our ugly number, 4.093 times 10 to the negative third squared over 0.946. Math happens here. Should arrive at 1.77 10 to the negative fifth. So what we did is we used the pH to give us information about either hydronium or hydroxide, whichever one we happen to have in our table. And we put that information in here under the equilibrium column, and we put our initial concentration under the I column. So far, so good. I've got one more for you. This one says it has an acid. The pH of a 0.5 molar HF solution with a Ka number that equals this. And again, I know in my heart that HF is an acid, but if you don't know that, you need a way to figure it out, and you can figure it out versus using the Ka. So the Ka is 7.1 times 10 to the negative fourth. And remember how we discussed the strength of a conjugate acid-base pair? We said whichever number is larger, the Ka or the Kb, that's the one that's strongest. That's the one that defines what kind of a compound it is. So we can find our Kb by taking Kw over Ka, like we showed in the last video. And if you do the math, you should get 1.4 times 10 to the negative 11th. And then we can see that 10 to the negative fourth is greater than 10 to the negative 11th. So our acid is going to be the stronger piece. So that means that HF is a weak acid. All right, now that we know it's an acid, we can do an ice table. We always use acid ionization reaction or acids. Okay, we'll do the specific one here. So HF aqueous plus water as a liquid goes back and forth from conjugate base fluoride and hydronium. And we'll just go ahead and put our squiggle in for the water. We have the initial concentration of HF, so we'll put that in the I line. We know we have 0 of the fluoride at the beginning and approximately 0 of the hydronium. And now, knowing that this is a weak acid because this isn't in our table that we memorized, weak acids are going to have X. They're going to partially dissociate. And we don't have a pH, so we can't fill anything in on the last line. So we just have to add down with what we've got and skip to step 3 and set up our Ka. So our Ka is going to be fluoride times hydronium divided by HF. We leave out the water. And we can plug in our E line here at the bottom. So that's going to be X times X divided by 0.5 minus X. And we have a value for a Ka this time, which you almost always will. 7.1 times 10 to the negative 4th. And then remember when we talked about the assumption, how we can use the assumption to simplify our math. Let's go ahead and try that and see if it works. So we're going to try using the assumption and we're going to document it so we don't forget that we used it. So we're going to assume that X is way, way smaller than 0.5, that number it's being added or subtracted from. So we can simplify this reaction to be X squared over 0.5. Just totally drop the X equals 7.1, 10 to the negative 4th. Okay, our math is looking a lot easier now. We can cross multiply. We can add this. This was the assumption. Okay, cross multiply. Math happens. We should get 3.55, 10 to the negative 4th. And if we take the square root of both sides, we're going to get a positive and a negative answer. But we can tell from here that we need to toss the negative answer and just keep the positive one. We should get 0.0188 molar. And before we keep that, we use the assumption. We need to check the assumption. Scout's honor, we always have to do that. Okay, so checking our assumption means we're going to take whatever our value for X is, and we're going to divide it by the initial concentration of our HF. So 0.0188 divided by 0.5. 0.5 being the number we simplified it to, and X being the number we eliminated. And we'll multiply that by 100%. Math equals 3.8%. Make sure you remember to multiply by 100 or all your error is going to seem really small. And we said we will only use the assumption when our error is less than 5%. And that's true. It is less than 5%, so we'll keep it. All right, so step 1 is to figure out the shift. Step 2, the ice table. Step 3, define X. Step 4 is to answer the question. So the question says to find the pH. So this is new. Usually the question in the last chapter just asked for the equilibrium concentrations. Now we need to go one step further and find the pH. And for some reason I'm writing over here, so I guess we'll just keep writing over here. So we know that the pH is the negative log of the hydronium concentration, and we happen to have hydronium concentration. It's equal to X, so it's equal to this number. So we'll take the negative log of 0.0188, and you and your calculator should arrive at a pH of 1.72. So you'll need to be flexible. Sometimes you'll have a piece of information like the pH or the pOH that you can't use because your equation has hydronium concentration or hydroxide concentration. Just be prepared if you need to make modifications to figure out what to plug in here into that sweet spot in the equilibrium under the ion. So that is all the information you need to know about ice tables when there is only one compound in solution, one weak acid or one weak base in the solution.